Thank you very much. And thanks, Julian and others for having me here and for organizing this seminar series. I think it's very nice and useful. And I will be talking today about this work with two great collaborators that are here in Dublin, Ivan Gusev and Andrei Parnachev, and the topic is finite temperature two-point functions in holographic CFTs. So before I start, let me just mention this is based on a paper which is kind of a part two of two related papers, and the first was already presented by Andrei in July in this seminar series, and it also draws on some ideas from the work that Sam presented in February. So you can take a look there for things that I will go briefly through. And also this is, I'm sorry for the repetition, but I will repeat some things from the talk I gave in Neurostrings, but I will try to also add some insights. So if you watch that talk, hopefully there will be also something new. So now to properly start, for me, some of the main motivations to look at CFTs at finite temperature are the following. Starting from roughly 40 years ago, we understand that constraints on manifolds that are not flat space are quite powerful. And the classic example is given by the torus in two dimensions. So there we have modular invariance of the partition function, and this leads to the Cardi formula for the density of states at high scaling dimensions. And these ideas work in slightly modified form, also in higher dimensions, and give some beautiful formulas for asymptotic behavior of both the spectrum and the OP coefficients at high dimensions. And to access these CFT data, one looks at these thermal geometries, which include the thermal circle S1, and then the most standard two geometries are either the sphere or the flat space. But this is a part of a more general program where you could also think of other geometries and try to formulate some crossing equations that would involve several correlators on different geometries. And this, for me, is quite an interesting subject to explore, where you could maybe draw something like this and study Bootstrap with
Sorry, can I already interrupt you? Sorry for that. So is this done, for instance, in 2-dimension? So I know there is modularity on one side, I know crossing. I mean, I guess the two cylinder are at KMS.
Exactly.
But was this done properly? So view as a matrix which is definite, positive definite?
So I don't, not to my knowledge. So Yixin, who gave a talk in the Bootstrap this year, where part of this was discussed, but it's unpublished yet. So I don't, yeah, maybe there is some work on this, but not that I know of. But definitely people are thinking about it, I think.
Okay, thank you.
And sure. And also, this is very general, but another parallel set of questions is what happens in conformal field theories that have sensible gravitational duals, and can we find some signatures of gravity in thermal correlators? And we know that there are some conditions on CFT in order to have a dual that resembles Einstein gravity. For example, it has to have a large number of degrees of freedom. Also, in the thermal context, there are so-called bulk cone singularities, which appear where you can connect two insertion points by a null geodesic in the bulk, as opposed to just a null line on the boundary. So you might wonder, and there are also other signatures like quasi-normal modes, and you may wonder if you can also kind of detect presence of black holes starting from the boundary by considering the CFT on the boundary. And okay, maybe this is not a conclusive answer, but these are some questions to keep in mind for the analysis that I will do today. So the topic, the main observable that I will be studying is a thermal two-point function in a holographic CFT. So the setup that I'll be considering is as follows. We look at this most standard thermal surface S1, the thermal circle times RD minus 1. So beta is the inverse temperature, and in this talk, D is equal to 4. So we work in 4 dimensions, and then we look at two-point function of scalar operators. We will simplify further by making the operators putting them at the same spatial point x, and then they will only differ in their time coordinates. So then this two-point function becomes a single variable function of tau, and it satisfies two interesting properties. One is conformal block decomposition, which is the composition in powers of tau, and the coefficients in this decomposition are dynamical, and they are called thermal coefficients of these A's. So there will be something that we want to determine. And then there is another condition called Kuba-Martin-Schwinger condition, KMS, which is true in any quantum field theory at finite temperature, and this is periodicity in Euclidean-time. Or you can also write it in this way, that G of tau is equal to G of beta minus tau. And because blocks are not individually KMS periodic, then the combination of these two constraints gives you some conditions on the coefficients A delta. And exploration of these conditions is often called the thermal bootstrap. And well, as also the organizers of this seminar know, the thermal bootstrap is a rather successful method, and it has been applied to the Ising model and to ON models. And these results in the models for various OP thermal coefficients are in pretty good agreement with Monte Carlo. So in this talk, the theory that we'll consider is of a slightly different nature, and it will be holographic. And what I mean by holographic is, on the operational level, the following. We'll think of this phi as some single trace operator and postulate that in the OPE of phi with itself, there are only two families of operators beside the identity. So one is double trace operators built out of phi, and the second is the stress tensor and its composites. And in large N-gauge theories, these are indeed the two families of operators that contribute at the leading order. And they have conformal dimensions 2 delta phi plus an even integer, and then 4n. So this delta t doesn't mean delta of the stress tensor, but it stands for generic composite operator built out of stress tensor. And so it happens that the thermal coefficients of these guys A associated with stress tensors are something that you can compute by analyzing the bulk equations of motion, and I will review this. And up to this work that we did with Ivan and Andrei, very little was known about the double trace operator. So this is the aim of these works was to compute the thermal coefficients of double trace operators. And because these are the only remaining operators in the two-point function. This essentially then gives the whole thermal two-point function in this case. Okay, so that's the goal, and the plan for the talk is as follows. So I'll first review these multi-stress tensors and how they are computed by solving some partial differential equations in the bulk. And then I will turn to the double trace sector and discuss first the general way how they're obtained, and then the concrete implementation, including numerics that we used in this paper. And I will conclude with some open questions and perspectives. Okay, so of course, if you have any questions, just interrupt me. So to start with the stress tensor sector, there is the following prescription for how to find this coefficient. So the thermal state is described by a planar Schwarzschild black hole, and this is the metric, and this mu is related to the temperature in some simple way. So this is the only parameter that appears here. And if you write the Klein-Gordon equation on this background, it turns out that you can perturbatively solve the equation in the ansatz of this form. So these R, W, and rho are some other coordinates, combinations of my original coordinates. And when R goes to infinity, that is the boundary. And so this is kind of a near boundary expansion. This coefficient ijk go in certain range, but I starts from 0, so I is controlling this expansion, let's say. And when you act on this ansatz by the Laplacian, you get the same form, function of the same form, and this gives you recursion relations for these coefficients ai, jk. And by solving order by order, you can proceed to any desired order. What you observe when you then push this ansatz to the boundary is actually that you will only get blocks corresponding to stress tensor operators, multi-stress tensors. So the interpretation is that this ansatz only captures the so-called stress tensor part of the two-point function. So in the conformal block decomposition, it would only include the stress tensor blocks. Okay, so to access double traces, you instead need to proceed numerically, at least up to now. No other ansatz is known that would capture both sets of operators. And there is a work by Parisinsky and Withers who developed a numerical approach and computed the lowest lying double trace operator by solving this Klein-Gordon equation numerically. Okay, so this is a little bit technical, but I wanted to include it because it is important for this paper, these recursion relations. Let me just briefly say how it works. So each of these terms I can call Fijk, which are these monomials. And when you act with the Klein-Gordon operator and multiply by a certain simple factor to kill off the denominators, you will get 11 terms. So Fijk, again, with these indices shifted by 0, 1, or 2. And then the way this works is that you consider these points ijk as forming some grid in 3D space, and you can express some extremal point of the grid in terms of the remaining 10 points here, and this is the recursion relation then. And then you just apply this formula over and over again to obtain all the coefficients in the expansion. And for the lowest orders, you can also not go through this, but it will turn out that we need quite a few of these coefficients. So the recursion relation method is really the way to go when you need many coefficients. And this is inspired by some similar works in conformal Bootstrap community, where conformal blocks have similar type of expansions in what is called radial coordinates. And here are some references for these works. Okay, so I won't say more about this method. So what was noted in this paper from last year was that when you compute a lot of these coefficients, so I didn't say, but a particular subset, so these coefficients with indices n0 to n are the thermal coefficients of multi-stress tensors. And when you compute a lot of them and just inspect the behavior, you will see that they exponentially grow with this power -4 to the n, and then there is a power law, n to 2 delta phi -3, and then there is some coefficient multiplying this. So this led to the following observation, that if you just sum this with blocks, there will be a singularity in the complex tau plane, which is closer to the origin than the singularity at tau equals to beta. We know that there is a singularity at tau equals to beta because it is the image, KMS image of the singularity at the origin. But this singularity is closer, and based on some general arguments, it's not supposed to be there in the full correlator. So this is not necessarily a problem because, as I said, we are only looking at stress tensor sector of the correlator, but is also showing that there needs to be something more to cancel this singularity in the full physical correlator. And well, there in this paper by Fitkovsky and company, they have this simple argument why this singularity is not there. So as I said, you can just ignore all this discussion and proceed numerically like in this paper, but the problem is that the numerics is maybe good for a first couple of coefficients, but I don't really see a way to push this numerics to determine something like the 5th or 10th double trace coefficient. So this is the reason why we will proceed by kind of field theoretic arguments. Okay. So the focus of our approach is on KMS invariance and this interplay of KMS and conformal block decomposition. So to derive some rules, what you can do, for example, is take the derivative of the two-point function at the crossing symmetric point, and all the derivatives are 0 by the KMS. And now when you decompose this in blocks and act on blocks by this derivative, you get a linear system involving thermal coefficients. And if you assume this holographic spectrum, so consisting of double traces and stress tensors, then this system takes the following form. And I took on the left-hand side all the double traces, and on the right-hand side all the stress tensors, and I will consider the stress tensors as known and double traces as variables that I wish to solve for. So this is an infinite system of equations, because for each k, this is the k that appears in the order of the derivative, you get one equation.
N equal to 0 is the identity, right, in this equation?
N equals to 0 is the identity, yes. And just for convenience, we'll rescale this coefficient A in a certain way. So the true thermal coefficients have this more elaborate index, but AM are rescalings of them that are more convenient to work with. Okay, so now the idea that we follow is to take this linear system and try to solve it. And it's an infinite system, but it has quite a lot of structure. One, it is upper triangular, and two, it is a toplets. If you write it in a matrix form, it's a toplets matrix. So that means, so upper triangular, it's clear what it means, but toplets means that it's self-similar. So if I look maybe from the second row and second column, I get again the same matrix. Which means if I solve for the first coefficient, I can solve for any other coefficient by just making some shift in the index of on the right-hand side. And these f's on the right-hand side is whatever was here on the right-hand side. Basically, it's composed of, so I just rewrote this system in a matrix form. So this is some combination of gamma functions and these lambda ends. Okay, so, yeah, this structure allows, and the upper triangular structure allows to solve by backtrack substitution. So it's very easy to solve this system, and you get this expression for coefficients an. And you see this m only enters on the right-hand side as this shift of the f. So the problem with this solution is that actually when you plug in values for some known theories, for example, generalized free field, this will diverge. So it's a formal solution, but it's an infinite sum, and then you need to do something with it. Yeah, find some regularization or something. And to a large extent, the rest of the talk is making sense of this sum and then seeing what the results are. So in the first paper, we noticed that you can try to Borel resum this. And okay, so this is, what does it mean? These coefficients you promote to some variables, and then, sorry, to functions by multiplying them by powers of a variable. So you promote them to generating functions essentially. And then you take the Borel transform of this function and the inverse Borel transform. So here are in green in this equation, the elements that implement this. So I divided by some 2k factorial, which will be which is somehow the growth of these coefficients, which makes the series divergent. There is some Borel variable t, and then the inverse transform is this integral. And we propose this should be the way to interpret the formal solution from above. Okay, good. So this is something. So let's check how this procedure works. So if you take the generalized free field and apply this procedure, you get the correct coefficients that were known from before. So this is nice. Then a more interesting check is the so-called asymptotic model. In this model, we take this asymptotic behavior of stress tensor coefficients that was observed in this earlier work and promote it to kind of an exact formula down to n equals to 0. And if you have a model which has these exact stress tensor coefficients, then in the equations, you can actually compute exactly perform exactly the integrals and the sums and compute these coefficients am. And then what you can do is you can recover the full two-point function as a complex function of tau, as a function in the complex tau plane. And this function has the following properties. It's KMS invariant. This is kind of by construction and has holographic spectrum. But importantly, it doesn't have any singularities in the complex strip from 0 to beta. And it is also bounded, so it also doesn't have a singularity at tau equals to infinity. So it's bounded as imaginary tau, imaginary part of tau goes to infinity. And you can write for any half integer delta phi an explicit formula. Well, maybe not for generic, but if you go one by one at half integers, for every half integer, you can run through this procedure and compute exactly this two-point function. And so somehow Borel resummation knows about the analytic structure of the thermal two-point function.
Can I ask something?
Yes.
On the slides before, is it bounded for every delta phi? Because I remember in your first paper that for the 5 case, it was not bounded. Am I remembering this wrong?
Right.
So it was a different method, right?
Yeah, no, that's a good point. It's not bounded for a delta phi. I was somehow thinking of 3/2, which is my main. Indeed, this depends on delta phi.
Oh, okay. So my second question was whether we should expect the asymptotic model to be a consistent model. If you take everything together, it's not clear. Right?
Yeah, it's a very good question, and our understanding is that indeed asymptotic model doesn't capture this property. So because this property is somehow sensitive to low-lying thermal coefficients, and it will be violated in general by the asymptotic model. Yeah, that's a very good point, which, yeah, I should have said. Thanks. Okay, so this is just some expressions to show that how this function, thermal two-point function, looks in the case where delta phi is equal to 3/2. And if you go and compute then the double trace coefficients, well, okay, we already anyhow, if you take the double trace coefficients of this two-point function and look how they behave as m here becomes large, so as the scaling dimension becomes large, they will have this sign alternating behavior, and there will be exponentially growing. So it's quite interesting maybe to compare this to ON models, Ising model, where you will have kind of exponential decay of, or well, I don't know if exponential, but certainly decay of thermal coefficients. And here they are growing, but they are canceling each other by these signs. And okay, this is not terribly surprising because we knew that somehow these double trace operators needed to compensate for this singularity produced by stress tensors. So this was to be expected, but it's also nice to see it in these explicit expressions. Okay, so let me now go to the last paper and discuss the question: what if we want to improve? Can we do better than this asymptotic regime? And can we somehow compute this exactly or exactly up to numerics? And what we will do is we will solve the KMS sum rules where the spectrum is supposed to be the following. So we take the exact formulas for lambda n's that we get from this bulk equation up to some capital N, and then we put all the higher stress tensor coefficients to 0. And then we compute the double trace coefficients. We get some number, and then we will increase n and see if this procedure converges and how well it converges. So in order to do this, you actually need to, so this procedure naively doesn't converge at all. Yeah, what you need to do is the following. So when you do this, a certain number of operators, let me just go quickly back in this formal expression, certain number of operators will give divergent contributions, a certain number of operators will give convergent contributions. So for example, if I stick to this case delta phi equals 3/2, then the identity will give a divergent contribution and all other operators will converge. So we already know how to solve this. So this can be Borel resummed as here. And this Borel resummation you can perform then for fixed n. And you will get some expression for a double trace coefficient, which will depend on n. But then when you increase capital N, the result doesn't converge, and in fact it goes as 4n factorial. So in order to make sense of this result, we performed another Borel resummation, but also using Pade approximation. So we took this an result that we got, promoted it to a function, then we take a Borel transform of this function, which produces a polynomial in the Borel plane. And then this polynomial is replaced by a rational function. And then it is this rational function that we take the inverse Borel transform of. And this gives a finite result for the OP coefficient. And this result depends on the capital N that we took. And this NG is just a parameter that, because we use some numerical method to do the integral, this is the parameter of this method. But this NG you can ignore, it's not important. What is important is how this number now that we get depends on the capital N. And we would like this procedure to converge as we increase n. So you can also reinterpret this as taking a sum over GFF type correlators, and this will be very much in line then with some of the works by Julian, Alessio, Eli, Denise, and Enrico. I think all of you are on that paper. But again, even if you reinterpret this formula in this way, still Pade Borel resummation is necessary to make it converge. Okay, so let's come to the results. Finally, if you follow this procedure and increase n, we see that it actually converges very well. So these are some examples of double trace coefficients. And you can see already the y-axis is, these differences are quite small. And this is maybe the main result, a table of double trace coefficients that we got with this method. So here delta phi is 3/2, and the number of digits that is kept here is the number of stable digits under increasing n. So that's the meaning of how many digits we keep. And I should say we use the 300 stress tensor. So the input of this procedure is the stress tensor OP coefficients, and we use 300 of them for this table. And you can, there are similar results for 5/2. Yes. I mean, ultimately they should start oscillating in sign. So for low values, they turn out to be positive, but when delta becomes very heavy, then you should see this oscillatory behavior. Yes, exactly. Yeah.
I have also a quick question about this slide. Mm-hmm. The stress tensor coefficients that you use as input, is it asymptotic, or is it now the exact from Fitzpatrick one?
These are now exact from, well, yeah, from this method, Fitzpatrick-Huang method, yeah.
Yeah.
Okay, so now I actually come to Julian's question. And indeed, the asymptotic model for delta equals to 5/2 gave a 2-point function which violates this boundedness property as you go to imaginary infinity. But the numerical 2-point function, this is for 5/2, doesn't violate. So this is of course you don't have an exact, you have to truncate, but this is pretty stable under including more terms. So indeed it seems that this behavior is highly sensitive to low-lying double traces, and it is resolved in this numerical, more precise model. Okay, so this is also one kind of nice check of the procedure, but maybe the main check of the whole procedure is comparison with the Klein-Gordon equation, numerical Klein-Gordon. So numerical solutions to Klein-Gordon equation in the bulk. And because I think I have time, I can explain a little bit how we did this comparison. So we followed the method that was done in this paper by Parisini et al. To obtain numerical solutions, and with maybe some minimal modifications, but essentially the same method. And this green G beta of tau is the function that you get by this numerical method. And then, as I said, it's not too precise. It's hard to make this method too precise. So, for example, if you just tried to expand this and read off the coefficients up to high order, this would not be really feasible. So what we do is we will take all the coefficients from the Pade-Borel method, except for one, subtract from the 2-point function, and then try to compare this with the remaining one block with the coefficients that we left unknown. So this is the idea. And okay, let me start with the lowest double trace coefficient. This one is actually not determined by our KMS sum rules procedure, so it's but let me still start from this one. So here we subtract, I don't know, the first 10 to 20 blocks, something like this. And then the result for small tau should approximately be just the contribution of the first double trace, and then with corrections of order tau to the 14. So when you plot the left-hand side, you should find approximately a constant function, and the value of the constant should be this coefficient. And this, indeed, when you plot, you do get something that looks very much like a constant, and the number that you get is this, which is in good agreement with the result of this paper. Not too surprising because it's essentially the same method. So anyhow, but maybe to check the consistency of our method, we need to go to higher coefficients, which are fixed by Pade-Borel. So I will just explain for one of these. And then all the others work the same. So we want to eliminate all the noise that comes from the first coefficient that we don't know. And this we can do by taking the derivative. So essentially this coefficient came with some power of tau. So if we take the derivative, we can eliminate this coefficient. So we take again this numerical solution, we subtract the low-lying blocks, and we take the derivative so that this term doesn't contribute. And the only block that we didn't subtract was the second double trace operator. So again, the result should be approximately a constant, where now the constant is the second double trace coefficient. And when you plot this, indeed, you see something that looks like a constant, and the value looks to be 7.7. And now we want to compare this value to the Pade-Borel value that we obtained before. And just to illustrate what I mean, when you plot the numerical Klein-Gordon, when you plot the left-hand side here, these are these black dots. So you get something that looks roughly like a constant. But the precision of this equation is not such that you can really make these points lie on a precise line. And then this black estimate is kind of the best estimate of what is the value of the constant drawn from these points. And then this green line is the Pade-Borel value, which is independently determined. So you see that they're relatively close to one another. And in this table, we put the numbers for various coefficients obtained by this method. And you see, so these first two columns show the Pade-Borel value and then this PD value. And they are quite close. So here I also include the asymptotic model value, which does quite well for this particular example, but this depends on value of delta phi. It doesn't have to be so good. And also GFF. And GFF is just to show that the result is actually quite different for holographic coefficients compared to GFF coefficients. And I should emphasize that the difference, our view of these things is that really the numbers that we obtain come with many digits, which are in this table. And so this comparison with the differential equation is just a sanity check, and it shouldn't kind of be read as the precision of the numbers of the Pade-Borel obtained numbers, but it's really because the partial differential equation can never reach that type of precision, but it's really a sanity check of the method rather than anything else.
Can you also estimate an error on the Pade-Borel? So can you try to include more operators and see if it is converging, try to extrapolate, for instance?
Yes, it's not so trivial. So yeah, it's not so easy because we would have to estimate how the coefficients themselves behave.
So for instance, for these two curves you draw there, the two plots, it seems reasonable to imagine that there is like a plateau at some point or like a possible extrapolation to do.
Oh yeah, I mean, we can do. I mean, I think this is the thing that we are doing here is like keeping the number of stable digits. I think this is kind of a reasonable heuristic way of determining the error. Really precise way is you would have to kind of rigorously estimate what you are missing by putting these lambda n's to 0. And this, I think, is quite tricky to do precisely, but maybe it can be done.
Well, one option, I don't know if you tried, is also to insert the asymptotic value for the one that you don't compute.
Yeah, so we actually never did it, but indeed, this is a very natural thing to do. Yeah, okay. I agree. So, okay, this is results for 5/2. You see, the agreement is not as good, but as I was saying, so this is the interpretation is that this is really due to the inability to solve the partial differential equation very precisely, but still there is some general agreement between these numbers. Okay, good. So it appears I have quite a bit of time, but okay, still I can conclude. So we, yeah, let me just summarize briefly and then say a few the directions that we are thinking about. So we use this method based on KMS sum rules, and there are essentially two main ingredients. One is some linear algebra and ways to write a formal solution, and then the second ingredient is how to regularize the solution and make it convergent. And this Pade-Borel procedure seems to do the trick. We applied it to these holographic CFTs and obtained these low-lying double trace coefficients with what seems to be a fairly high degree of accuracy. And on the other hand, for the heavy double trace coefficients, the asymptotic model should provide a good understanding how they behave, in particular this asymptotic growth with alternating signs. So yes, there are several things that one can try to do in addition. Certainly, it's possible to analyze similar questions with finite x. It makes the analysis more difficult, but many of the ingredients are there. And in this way, one would probe the double trace coefficients of so the coefficients that were computed here are averaged over all spins or summed over all spins, but here we would be computing them for each spin separately. And then if you go to finite volume or consider geometry as 1 times SD minus 1, these types of analysis should give you access to actual flat space Schottky coefficients, which I imagine would be technically considerably more difficult, but it's still probably doable. As for other dimensions, so this was all in 5 dimensions in the bulk and 4 on the boundary. As long as this Fitzpatrick-Wang ansatz works, everything else should follow. So far, it's known how to do this ansatz in even number of boundary dimensions. So for odd dimensions, it would be interesting to see what can be done. So, okay, there are some interesting questions. What can we learn from these 2-point functions? Can we compute Lanczos coefficients or quasi-normal modes? Can we, and this brings me back to this question in the introduction of signatures of holographic against non-holographic correlators. One interesting model to compare with is ON at large n, so it has a large number of degrees of freedom, and it has a very similar spectrum, but the thermal coefficients behave in a very different way, so maybe this behavior is something to look into. Also, an outstanding question is to understand these results from purely field theoretic analysis in maybe n equals to 4. This would be quite interesting, but it's probably very hard. And then also to explore other CFTs, particularly at large n, and see which properties that we have here will be modified, which will remain. Yeah, all of these are, I think, interesting things to explore, and then also to go beyond large n, but that is presumably quite difficult. So with this, let me thank you, and yeah.